So you have the floor.
And good afternoon. I'm Giovanni Cappelli. I got a doctoral research in agricultural ecology at the University of Milan, and I'm currently working at CREA with Marcello Donatelli, and my research interests mainly deal with the development and the evaluation of crop models, as well as their application large scale under climate change. So this presentation is aimed at sharing some methodologies and some generic methodologies for assessing climate change impacts through the use of process-based models. Where I can, dove devo puntare?
No, all'incontrario.
Ah, okay. Okay. The presentation, this presentation is account for 5 sections, and we start with a short introduction about the simulations model. And process-based crop models are mathematical representation of the dynamic interactions between plants, weather, soil, and farming practices. That means that they are software applications that implement chains of interconnected algorithms which are meant to build a storyline of the agricultural systems with model outputs as the values of the state variables over time. Compared to empirical or statistical approaches, they allow understanding and extrapolating the underlying mechanism and relationships which regulate a subsystem. And so they foster the applicability outside the condition for which they are calibrated for. But also they allow to build bridges with some domain specialists and scientists dealing with the field or under control experiments. Since the 60s, they have been largely used to understand and quantify the trade-off between productivity and management at field and large-scale applications. But they evolved over time to tackle emerging research questions, mainly dealing with the mitigation of greenhouse gas emissions, the enhancement of the ecosystem services and the environmental performance of the agricultural systems, and to reduce losses associated to pests and diseases, and to foster the improvement of product quality, and to design improved idiotypes, and to design adaptation and mitigation strategies to climate change impacts, thanks to their ability in reproducing nonlinear responses to boundary and unexplored conditions. Nowadays, we have a large number of crop models, but little emphasis has been placed on their improvement. Indeed, many crop models still remain black boxes coded in procedural languages with little documentation of how they work, and scarce control of simulation steps and quality of input-output. Obviously, this is not an efficient way of formalizing the complexity of biophysical interactions between crops and their environment. In this context, model frameworks have represented a substantial step forward with respect to monolithic implementation of biophysical models. And the main reasons are connected to the separation of algorithms from data, the reusability of services such as input-output procedures, data view, utilities, and integration services, and the isolation of a modeling solution in discrete units targeting reuse, and fine granularity of implementation, which allow extension, composition, and comparison of alternative modeling approaches or solutions. All these concepts rely on the principle of modularity. Modularity is the design principle of subdividing a system into smaller discrete units called modules, which can be independently managed, recombined, or used in different systems. Modular modeling facilitates the reuse, the scalability, the incremental improvement and maintenance of modeling approaches, opening them to the contribution from third parties. In this context, the object-oriented programming had a key role in fostering the development of large, flexible, and effective model structures by decomposition into smaller units, modules, which perform logically discrete functions and interact each other through well-defined interfaces. In this context, Meyer defined 5 criteria as good practices in modular design, which can reasonably be extrapolated to different modeling contexts. These principles are decomposability, composability, understandability, continuity, and protection. I don't give you more details because these are technicalities, but we can now move to the Bayona Platform, that is a software framework designed to develop, analyze, and run modeling solutions on a generic spatial units, and is currently used by the Joint Research Center of the European Commission for Yield Forecasting. Within this framework, the cropping system is divided into different domain-specific compartments. For example, we have the crop, soil, agro-management practices, which are coded separately in independent software units named components. Model components can then be interlinked into more complex simulations chains aimed at solving specific modeling goals and coupled with a spatially explicit database with information on climate, crop, and soil properties. The modeling solutions manages the simulation time and the call order of the simulation components within a time step, which is usually daily, but it can be also hourly. It depends on the process we are considering. The modeling solution can be run via sample console application or run in Bayoma applications, such as Bayoma Site or Bayoma Spatial, or using dedicated adapter. So this is the general scheme of the Bayoma implementation. And we had a model layer which refer to the components, so the single components. And then these components can be composed in a more complex modeling solution, which refer to the composition layer. Then this modeling solution can be can communicate with advanced functionalities such as tools for sensitivity analysis or optimizers, and can be used within some console application. And the platform provides also some developing tools which consist of mostly code generators which support the programming activities. How I said before, Bayoma is grounded on the software components of the model layer, and now I list some key concepts. And a Bayoma component is a library of simulation models related to a series of processes that take place in the agro-ecosystem, such as crops, insects, plants, and diseases. And each component consists of 2 discrete subunits. And the first one consists of interfaces and domain classes, which allow the definition of the domain, which contains the input and the output variables from the models. And then we have the strategies, which includes the models and or in other words, the algorithms, parameters, and the control of pre and post conditions. And both of these units are extensible. That means that new variables can be added to the domain and alternative model approaches can be implemented. So the components can be used standalone or integrated in Bayoma modeling solution, as said before. So this is a general scheme or representation of generic modeling solution. In this case, we have a component that is aimed at reading weather data, so radiation, temperature, and precipitation. Then we have a component specific to reproduce the impact of farming practices on the system. And so, for example, we have sowing date, cultivars, or irrigation techniques. And then we have a specific model for growth and development. So we can simulate the phenology, the leaf area index evolution, the above ground biomass rates of accumulation, and potential transpiration. Then, if we are interested in considering also limitation due to water availability, we can link also a module specific for the simulation of soil water. And so we have an estimation of the evaporation, of the soil water content, and water uptake. On the right, we have a detail of the growth and development model. This is the UniFi grape model developed by the University of Florence. And as you can see, all the processes considered are encapsulated in separated modules. And for each module, we have alternative approaches, which mean modularity and fine granularity of implementation. Then this is approximate. Here we have all the components that are developed for Bayoma, and if you want, you can retrieve some more details on the Wikipedia page. Then now I show you some example of methodologies to build a simulation framework to assess climate change impact on crops. And okay, spatializing crop models requires information on the heterogeneity of pedoclimatic conditions and management within the simulated geographic region. Such data need a level of detail that is consistent with model requirements and studies objectives. And in this context, the minimum input dataset includes information on environment, management, and crop type and distribution. Obviously, this minimum dataset depends on the simulated production level. For example, we can consider potential versus water, nitrogen, or disease-limited productions. For example, in water nutrient depleted production system, additional data are necessary in order to set soil conditions at model initialization. Furthermore, model application in climate change impact assessment requires additional data concerning future climate projections, atmospheric CO2 concentration, and information about adaptation strategies. And also data to perform a model calibration, which is the check of the validity of the model at a different spatial scale, are needed. But this information related to the main phenological variables, growth dynamics, and crop operation is rare at this scale. But in this case, we can rely on different procedures that use some proxy variables to replace this data. Okay. Most of the existing simulation studies rely on a minimum data set in the areas of interest, and in this context, the study area is divided usually into a finite number of smaller areas, called the simulation units, that are characterized by homogeneous pedoclimatic condition and or cropping systems. Then these data are georeferenced in a multi-layer and spatially explicit database and univocally assigned to each simulation unit depending on spatial attributes, so geographic coordinates of the centroids via the use of GIS-based software applications. And we have on the right an example about the tomato cultivation area in the southern of Italy. And environmental information often relies on data of different resolutions, which need therefore to be aggregated or disaggregated before being used via dedicated procedure. And this information can be replaced by proxy variables obtained by pedotransfer functions, as in the case of hydrological properties computed from soil texture, or the use of remote sensing data. Okay, now this is a scheme of some of the most advanced procedure to realize a framework for climate change assessment. And the first step is aimed at build a georeferenced database with information of crop management, current weather, and future scenarios, and also with agroclimatic data as crop distribution maps, and soil data, and the main data refer to texture and hydrology properties. Then the database is linked to a modeling solution which implements some biophysical model to estimate the development and growth, soil hydrology, and farming practices. And then, after simulation, we can explore the variability of output variables within and throughout the study areas. And also we can store the results on a specific database, which can be on clouds or... And, okay. About input data, the first step is to define a procedure to build a suitable and plausible projection of future climates. Often, climate change impact studies are carried out by adjusting historical data with outputs from the ZCM models or generic effects. But the generation of synthetic weather series via stochastic weather generation is intended to be statistical representative of future climates, and so is more advanced. And the IPCC scenarios represent possible paths of socio-political and economic drivers of change. And ZCM are some estimates of changes corresponding to the future atmospheric greenhouse gases concentration and radiative increases associated to a given IPCC scenario. In these cases, obviously, the baseline should correspond to a time frame roughly contemporaneous with the time of the research and with the time horizon at which the daily data anomalies refer. And in this context, a minimum of 20 years is deemed large enough to parameterize weather generators, since allowing to capture the most part of the less frequent events in a area. And obviously, is necessary to perform a bias correction and downscaling procedure to accurately and reliably apply core-scale derived information to a finer temporal and spatial resolution, and to solve important subgrid scale issues related to clouds or topography via spatial downscaling. Then, for what concerns the crop management and agroclimatic data, Usually we can extract some data from the global, regional, or local databases. But when these data are not available, we can use some techniques such as remote sensing to derive this information. And we have here an example of the processing of multi-temporal analysis of historical MODIX data, which allow us to derive the rice cover percentage in the Lombardo-Piemontese district. But other methods can be based on literature or on expert opinion, and so we can define some rule-based information. In this case, we derive the tomato cultivation area considering an upper limit threshold of 200 meters above the sea level. And then the processing of MODIS data allow also to derive some information related to the management, so as in this case the sowing dates, but also on the phenology of the crops. In this case, for example, through the processing of the a dynamic of the vegetation index, we can derive some indication about the emergence of the crop or the heading, which correspond to the max of the curve, and also information about the end of the seasons. And then we need also information about the adaptation, which rely on the shift in the planting dates, in the adoption of alternative irrigation regimes, on the possibility to implement some chemical treatments, or also adopt some varieties with different cycle length, or improved varieties for some characteristics such as resistance to pests and pathogens, water stress tolerance, and quality traits. The first group can be realized by the definition of rule-based or fixed date rules, and in alternative we can consider some rules based on the state of the system, such as development stage, or I don't know, the water content in a given depth of the soil, the available water in a given depth of the soil. And we have here an example of sowing date for maize, which were estimated using a rule based on air temperature thresholds in the Lombardy region. Whereas the other group of adaptation strategies can be implemented by modifying model parameters related to the target processes. As last, it is important also to consider crop suitability to agroclimatic conditions when evaluating productivity potential of new crops and areas, or for the assessment of potential cultivation shifts and adaptation needs under climate change scenarios. In this case, in Bayoma is available specific components that implement 3 different approaches. An approach is the FAOECO crop, which is based on 2 response functions to temperature and rainfall during the crop cycle. Then we have the less favored areas, which evaluate the suitability of generic agricultural areas according to natural constraints related to climate, soil, physics, and chemistry. And then a multiple regression model, which uses the same information provided to the less favored areas criterion, but as regressor, and the cover percentage of a crop in a certain areas are dependent variable. And we show 2 examples. we have the application of the FAO crop methods to the Morocco, and we, as we can see, the only comparing our projection with the current crop mask of wheat in Morocco, the major errors of omission and commission rely on the Atlas mountain, and whereas we have also an example of the multiple regression methods, which is applied on the Tuscany region to identify which kind of variety is the best suited in different sites of the region. So, okay. And then we move to the results section, and I will show you some application of the Bayona Platform on other crops, mainly than grape. But what is interesting is the methodology, which can be then customized to explore the same model outputs for grape. So I will start with some results achieved for yield productions and irrigation management. And as said before, significant actions is needed to support the crop growers to enhance production levels while saving irrigation water in many regions worldwide. And climate change is expected to exacerbate the competition between countryside and urban areas for water use, even in water-rich areas. And for what concerns the grape, irrigation has been historically banned by the European Union's wine laws. Though in recent years, individual countries are reviewing their regulations, as Spain and France. Indeed, severe water stress can alter the components of the harvested grape, delay ripening, and induce the shriveling of the berries. For what concerns the evaluation of the impact of climate change on the water resources, we applied at the University of Milan the CROPSIS model, and we coupled it with a soil water model and applying them to analyze the sustainability of the maize in Lombardy under scenarios characterized by different combination of production factors and climatic conditions. Simulations were performed at agrarian region scale by implementing specific automatic rules to mimic for each simulation unit the main irrigation techniques according to local feasibility. And so, as it can be seen, with no adaptation, average decline of yield production was around 18%, with peaks of minus 23%. And adaptation strategy based on the adoption of early sowing of hybrids with longer crop cycle allowed to halve project losses. But of course, these adaptation strategies needed a huge amount of water, which ranges from 160 millimeters to 60 millimeters, depending on the techniques adopted. And also the water use efficiency was very different depending on the system adopted, and grow from about 2 kilograms of dry matter for cubic meter of water, moving from surface flow, and to 4.5 for drip line system. Then the surprising results achieved is that the maize in monoculture compared to alternative cropping system was the best suited in a very little number, in a very small number of agrarian regions in the plain of the Lombardy regions, because of the large amount of water required. So Then another aspect which is very interesting to inspect regard the simulation of the impact of diseases, and I will show you the results of a model for potential infections. This model simulates on hourly basis the response of a generic fungal pathogen to both air temperature and leaf wetness duration with an hourly time step by means of 5 parameters. And then it computes the risk of potential infection as the ratio between the number of events and the 24 hours. And here we have an example, and we can see the combination of temperature and leaf wetness value, which can trigger potential infection events for the blast disease in rice. But now we will see some example of simulation run at European level for Plasmophora viticola and Botrytis cinerea for grape. And here we can see the differences in the number of potential infection events simulated in 2030 compared to the reference scenario. And as it can be seen for Plasmophora viticola, is expected a general increase of potential infection ranging from the 5 and 20%, whereas for Botrytis cinerea the situation is more heterogeneous, and so we have some critical situation and improvements in the eastern part of the Europe, maybe because in these areas the temperature under current climates are close to the optimum, and so in future projections the situation will be better. Then, of course, these models can be used also to evaluate the risk of potential infection during the season, and this is an example for the infection efficiency patterns in the period June-August for the blast disease. And we can see that this risk is highly variable depending on the condition, on the climatic condition explored day by day. Okay. And these models for potential infection are integrated in a generic framework for airborne fungal plant disease, which simulates disease progress with an hourly time step, considering infection, incubation, latency, infectiousness, sporulation, and spore dispersal phases, but consider also the impact on the plant. And indeed, the percentage of dead tissue is used to reduce values of leaf area index and thus the above ground biomass storage and the storage organs. Of course, the application of chemical treatments can reduce the disease severity and so the difference between potential and diseased yield. Depending obviously on the principle used, but also on the moment of the season in which the product is applied. Then another aspect which is very important for crops, but also for grape, is crop quality. And crop quality represents an aspect scarcely investigated in crop modeling activities, but is fundamental to assess the economic and nutritional value of crop productions as well as their end-use destination. I'll show you an example for rice. In particular, we assessed the head rice yield, which represents the percentage of all kernel after milling, and is the main determinant of rice price at global level. Potential head rise is simulated as function of hourly night tire temperature during the grain ripening, and is then decreased when rainfall, wind speed, and temperature exceed critical thresholds. Here we have the simulation of head rise yield under current conditions, and it ranges from 59% to 64%, but in the future this variable is expected to decline with a pattern from the northwest southeast of the region according to the pattern of temperature increases. Then we have another example for tomato, and total soluble solids content represents the main indicator of tomato quality, as it is highly correlated with the sweetness and maturity degree and directly affects fruit acceptability to buyers and consumers. So the Brix degree is simulated depending on the cumulated actual transpiration and in the fruit set phase, and is modulated by the susceptibility to water stress and by parameters related to fruit development, growth, and quality. Here we have a projection of Brix degree for 2030, and for a crop which received an amount of water corresponding to the 50% of evapotranspirations. And as we can see, this is the Apulia region, and we have an heterogeneous picture with areas with increases for this variable, and also some decreases up to 5.75%. But what is interesting is that if we would like to apply more irrigation water to avoid possible incidents of possible reduction of yield due to water stresses, this is the situation, and this increase in water use will cause a general decrease in Brix degree. So considering quality is important to develop effective water strategies for a crop. Then, for what concerns grape, the achievement of high-quality products strictly depends on several fruit quality parameters, such as sugar amount and composition, Brix degree, tetrable acidity, or phenolic content. But available models deal with the simulation of sugar accumulation in the fruit and are based on allometric relationships or enzymatic kinetics. For the latter, the fruit is modeled as a single metabolic compartment, and reaction rates are proportional to the amount of reactant. And then there is a partitioning of carbon supply, which is transformed in glucose, fructose, sorbitol, and other compounds, which are mainly starch and structural sugars. And in this context, UNIFI is working in developing new models for fruit quality, focusing on Brix degree and acidity. And as last aspect, I will show you some results achieved for the impact of ozone concentration on crops. And at ground level, ozone is phytotoxic to plant and can cause substantial damages on crops, up to 30%, depending on crop susceptibility, weather condition, and farming practices. In general, factors which limit gas exchanges as water stress reduce ozone injuries. But the main damages on crops involves reduced photosynthesis, increased respiration, acceleration of leaf senescence, and development of foliar chlorosis or necrosis, as well as stomatal sluggishness, which means damage to the stomata due to ozone exposure. ozone chronic exposure. And here there is a scheme of the model we have implemented with the JRC to estimate the impact on ozone on wheat. And here we considered processes which limit photosynthesis, but also involving the capacity of repair tissues, damaged tissues. We implemented also the long-term effect, which involved the acceleration of luminescence and also the impact of water stress on stomatal conductance. And we coupled this model with the WOFOS model, which was developed by Alterra in the Netherlands and which is used by the European Commission to perform some crop monitoring and yield forecasting studies. And here we have some results from a simulation experiment carried out on wheat under growing ozone concentration. And we considered two different locations. One is Bremen in Germany and one Jerez de la Frontera in Spain, which are very different and have contrasting climate conditions. And as we can see, the exposure to growing concentration of ozone lead to growing losses in the wheat crop with peaks of 30% in rain-fed condition in Bremen. And also in this case, the application of irrigation exacerbates the losses due to a higher flux of ozone which can reach the plant. And okay, this aspect is also important for grape because the chronic exposure to ambient ozone, partial pressure, reduces net CO2 assimilation rates in between 5 and 30% compared to the control, but also the exposure to acute levels of ozone decrease grape leaf photosynthesis due to a reduction in both stomatal and mesophyll conductance. So I conclude, and the assessment of the sustainability of agricultural systems under climate change conditions highlight concrete problems, but also opportunities. The impact will be spatially variable and crop variety specific. Criticalities must be estimated locally, developing specific adaptation solutions. Besides the mere productivity, the consideration of fruit quality and of yielding factors related to water availability, diseases, pressure, and air pollution will be crucial. Systematic efforts to integrate knowledge and data from multiple stakeholders with simulation tools will be also crucial. And in this context, the modular structure of the bioma framework will allow to implement and compose customized modeling solution for grape at an optimal spatial resolution via the extension of existing components. Then the sub-project AgroModels, which is founded by the Italian Ministry of Agricultural, Food, Forestry and Tourism Policies, and coordinated by the CREA, will partly tackle some of these research topics. And the project is aimed at developing both real-time and scenario analysis support system at various levels and scales. And customized products, services based on the application of biophysical models will be realized with the aim of supporting the management of cropping system under current climate change conditions. And these services will be made accessible as they are through tablets or smartphone implementation, but also as data information that can be used in different applications. And the implementation of the open data standards is an added value of the project. And in this context, I think that it will be a room to collaborate with the Clim4Vitis project because we can share some technologies and knowledge. The project is already founded, so we can start. So. And thank you for the attention.
Okay, thank you, Giovanni, for your presentation. So we have about 10 minutes for question or discussion. If you have a question, please make the question now, and then I would like to start with the discussion. No questions? Yeah, very, okay. Oh, one question, good.
Hello, just a small question. Thank you for your presentation. I'm interested in your disease and pest and disease model for viticulture. And I'm wondering if it's available for the public to use or it's proprietary.
Yeah, it's free. You can find on the Wikipedia page, I show you all the publication which refer to this model. But this model is available, fully documented. We have some code documentation and also some application to show how to use it and how to couple it with some meteorological data and so on. So you can use it if you. It's free. See, through Wikipedia or the Bayona portal, you can access to the kit. We have the components, the documentation, the help, the code doc, and so on. All things needed.